Okay. We'll report progress on work done with collaborators, Ryan, David, and many others throughout the years. The motivation of this work comes from binary neutron star mergers. So the theory that describes the neutron star interiors is mainly quantum chromodynamics. And that theory describes the strong nuclear interactions. And it's difficult to solve, and there's a large degree of uncertainty with respect to the equation of state and the composition of neutron star cores. Nuclear physicists have come up with many different models that give different predictions for what the mass-radius relation would be for each equation of state. So this is a mass-radius curve for us. We have one curve for each equation of state. And you can see there's a large discrepancy between models. So for a given density, the pressure is unknown to maybe a factor of 2. With gravitational wave astronomy, people started thinking if we can use gravitational waves to place constraints on the neutron star equation of state. A few years ago, people working on post-Newtonian theory thought that these finite size effects of neutron stars would be negligible because formally they come into fifth post-Newtonian order. However, tidal effects are Newtonian effects. They're not fifth order post-Newtonian effects. So they come in with a very large factor of tidal deformability. So to answer the question whether this would be observable in waveforms or not, you really need numerical relativity. So the first simulations that try to estimate the measurability of these effects with gravitational waves were done in collaboration with Masaru Shibata in 2009. So we parameterized the neutron star equation of state. We used the piecewise polytropic formalism with 4 free parameters. And by varying the equation of state parameters, you can vary the tidal deformability of the neutron stars and how stiff the equation of state is. So for soft equations of state, you see that the pressure is low. The stars are very compact, since the pressure does not resist gravity very much. And so the waveform, the blue waveform corresponding to the neutron star binary, behaves mostly like a point particle waveform. And departs from a point particle waveform, shown here in the red dotted lines, later in the inspiral, just before merger. And after the merger, it collapses immediately to a black hole because the equation of state is soft, so nothing can prevent collapse. For a stiff equation of state where pressure is higher, there is an earlier departure from the point particle waveform of the same mass. And after merger, there's a delayed collapse to the black hole. So for a while, there's a hypermassive remnant that rotates, and once it emits gravitational waves and stops, it will collapse to a black hole much later. Okay, so the first such observation came in 2017, where we observed about 100 seconds of the inspiral, right up to before merger. So LIGO was not sensitive to frequencies above 400 hertz or so. So we missed the merger, but we came very close. So that observation contains tens of thousands of cycles of orbits happening within the last 100 seconds of the inspiral. So using this is a simulation done by Sean Rosowski at NCSA with the Einstein toolkit code of this event. Okay, so numerical relativity can only simulate the last few orbits, and usually we use post-Newtonian or effective one-body waveforms to model the early part of the waveform, and we try to calibrate numerical relativity waveforms with post-Newtonian waveforms to make sure that they're accurate enough for extracting parameters from events like this. Tentatively from this event, that's an early analysis. There's better analysis now, but this is from a paper by Nick Sturgiulas. You can place constraints of the equations of state and exclude very stiff or very soft equations of state from this one event. But you can combine this with other events and do better analysis now. Okay, so we know that there has been great progress, a revolution in the last years on the development of black hole binary templates, gravitational wave templates, but the corresponding work for neutron star binaries has lagged behind in accuracy, mainly due to the complications in simulating matter in numerical relativity. So the method mostly used by most, all numerical relativity codes is the Valencia formulation for evolving matter. So that involves conservation of the energy momentum tensor written in this flux conservative form. So that gives you the relativistic Euler equations together with a conservation of mass, rest mass. And you evolve that together with the Einstein equations in some formulation. Okay, so there are other formulations for fluids other than Valencia. I'm going to focus on the last one, on Hamiltonian formulation, because that's the one most relevant to this conference. So Carter has developed a super Hamiltonian formalism for barotropic fluids, and we're going to adapt this approach here to a constrained Hamiltonian approach for appropriate for 3+1 numerical relativity. Yeah. We can if we want to, but I'm not including it here. Yes, they're perfect barotropic fluids. Okay, so I'm going to call this approach acoustical and canonical fluid dynamics. So I call it acoustical because we replace the continuity equation with another equation that involves the Hamiltonian, that involves the acoustic metric. And the equation for the kinematic momentum is replaced by another equation for the canonical momentum, which is a Hamilton equation. Okay, so many decades ago, Carter and Lichnerowicz came up with a variational principle for barotropic fluids and showed that the motion of a fluid element in a barotropic fluid moves along geodesics of a manifold with metric h squared times g, where h is the specific enthalpy and g is the space-time metric. So this action is very similar to point particle action, except you replace the rest mass with a chemical potential or specific enthalpy here, and that can vary from one point to another. And the gradient of that chemical potential gives you the pressure force. We also know from the three theorems of Helmholtz, the third theorem states that initially irrotational flows should remain irrotational. And that's very relevant here because most numerical relativity simulations begin with irrotational initial data. That means that two stars, they go about each other like this. There's no spin. As opposed to a tidal lock system, for example, like the moon is tidally locked to the Earth, it would be corrotating. But for neutron stars, the viscosity is negligible, so there's no time for tidal locking. So if you start a simulation a few orbits before merger, there are no millisecond pulsars in binaries observed, so the spin will be negligible compared to the orbital spin. Okay. Okay, so these concepts can lead to Lagrangian or Hamiltonian or Hamilton-Jacobi schemes that can be used in numerical relativity. So I was at a restaurant in Milwaukee thinking about this problem when this song started playing. So I thought it was a sign that I should continue to work on this problem and not give up. Okay, so if you have that action, you can write down Euler-Lagrange or Hamilton equations of motion. So in the usual particle form, they're written like this. I should emphasize that this is a point particle action. I mean, not point particle, but a fluid element action. So it corresponds to one fluid element or one fluid particle. There's no Lagrangian density here. It's just a Lagrangian. So the Euler-Lagrange equations are written here in the usual particle form. And you can convert those to partial differential equations using a chain rule. So over here, this partial derivative takes a derivative of the Lagrangian for a fixed momentum. So L depends on x and p, and you just take a partial derivative with respect to x. But over here, the Lagrangian depends on x and p of x, or actually v of x, the velocity, as a function of x. So that's a covariant derivative, and effectively, the Lagrange depends only on position from one point to another. So when you take this covariant derivative and apply the chain rule, you can relate this with this. And this is the Lie derivative, and p is the canonical momentum. And you can do the same thing with the Hamilton equations. Use the chain rule to go from here to here. You can also use the Lagrange, the Cartan identity for the Lie derivative and express it in terms of the exterior derivative, and go from here to here directly in one line, basically. So it's basically immediate. Okay, so the nice thing about these equations is that they're written in covariant ways. So they're true in any theory of gravity. They're valid for Newtonian gravity and for general relativity and for any other theory of gravity, simply because they're just the Hamilton equations. The only thing that changes is the Lagrangian or the Hamiltonian and your canonical momentum. Everything else is, the equations themselves are the same. Okay, so for example, for general relativity, the H is the constraint Hamiltonian. It comes after you have imposed the constraint that u dot u is -1. And you get this expression. So that's, so if you set the mass, so if you set the pressure to 0, so the chemical potential is equal to rest mass here, and you go to flat space-time where the lapse is 1 and shift to 0, then you get Einstein's formula for the energy, that E squared equals P squared plus M squared. So that's a generalization of that formula in Kerr space and for a fluid instead of a dust. Okay, so H depends on position and time here. And you can compute the Lagrangian, and the canonical momentum is H times U, where U is the forward velocity. So again, H plays a role of rest mass, but it varies from one point to another. So the spatial components of the forward momentum are these, and the time component of the forward momentum, of the canonical momentum, coincides with that energy, or the Hamiltonian. Okay, in Newtonian gravity, the same equations are true, except now the Hamiltonian has the usual form of kinetic energy plus potential energy, and the potential energy is the Newtonian potential plus the chemical potential. And the gradient of that potential gives you the pressure gradient. And the Lagrangian is, and again, kinetic energy minus potential energy as usual. Okay. So in 1858, Helmholtz published his 3 theorems, and as I said, the third theorem states that initially irrotational flows remain irrotational. A few years later, Kelvin stated a more general theorem on conservation of circulation that states that the circulation around the ring of fluid that is dragged along by the flow is conserved. So that circulation integral, that means if the is conserved. So if the circulation is initially 0, then it should remain 0. So Helmholtz's theorem is actually corollary to Kelvin's theorem. Now, some books state that on classical mechanics, they talk about the Poincaré-Cartan integral invariant and state that it's similar to Kelvin's theorem, or Kelvin's conservation of circulation. Well, it's not similar. It is Kelvin's circulation. So we know that a system, a Hamiltonian system, a dynamical system has a Poincaré-Cartan integral invariant of this form if and only if it is Hamiltonian. And I just showed that a barotropic fluid is a Hamiltonian system, so it should have that invariant. And that invariant is Kelvin's circulation. So now Kelvin's theorem can be seen as a special case of this much more general theorem. So based on this observation, you can find several other generalizations of this integral in different systems. And we've done that in this paper. So we looked at magnetized systems. So if you looked at a barotropic fluid that's perfectly conducting or poorly conducting, you could write down a Hamiltonian and therefore derive circulation integrals like that. That are special cases of the Poincaré-Cartan invariant. And surprisingly, we also found that, again, for ideal MHD fluid in the baroclinic case, the motion is still geodesic, which was unexpected. But it's a geodesic of a metric. It's a Finsler metric now because it depends on velocity and the magnetic field. It's not a Riemannian metric anymore. Okay. So I'm going to focus here on non-magnetized fluids. So the equation, the Hamilton equation that I wrote here, if the initial data is irrotational, that means this vorticity term is 0. And then you just have this term plus this term. So it becomes a flux conservative equation in this case. And you can take a first integral of that. And the first integral is a Hamilton-Jacobi equation. So if you take the gradient of that equation, you go back to the Hamilton equation that I wrote before. So if you look at a pressureless dust, you can say H equals to 1. And that equation takes this form. This can be seen as the gradient of a relativistic Berger's equation. And that has been looked at numerically by Philippe Lefloch and collaborators. And they also looked at other versions of this equation in the Schwarzschild background or FRW background. I don't think they really realized that they were deriving the Hamilton-Jacobi equation. But they solved this equation numerically and showed that numerical evolution works, and they can even do shell capturing. So this is an encouraging sign for us. Now, it is well known that Hamilton-Jacobi equations don't have a unique solution, but they do have viscosity solutions. So solutions in the vanishing viscosity limit that are unique. I'm not going to do a proof here, but I'm just going to point to this article and some numerical evidence of this can be found if you take a fluid that has 0 pressure and moves with constant speed in one direction, and you start with that initial data and try to evolve this equation, then your code suddenly will jump to another solution that moves with equal and opposite velocity. And you don't have good control over which solution your code will pick. Well, if you evolve backwards in time, you're going to pick that solution. And that problem is similar to the problem that some of you are having with tracing black hole horizons. I think you have to evolve backwards in time. So that equation is very similar to that, except because the mass of the photons is 0, that term is 0, but otherwise it's similar. But if you add a little bit of viscosity here, then your code stays at the branch you started from. So that restores uniqueness. Okay, so I talked about the Hamiltonian form of the Euler equation, and now I'm going to talk about how to rewrite the continuity equation. So you can write it using the acoustic metric, and what that does is it makes explicit the dependence of the canonical momentum. So if you want to do characteristic analysis of this, it's much easier to work with this than with the original equation that involved the rho times u, the continuity equation. Yeah. You impose it as an extra condition that you take the continuity equation for granted. So that equation, let's see. So that equation contains coupling to the continuity equation through h. So the continuity equation involves rho through the equation of state that rho depends on h, the specific enthalpy, and so this is coupled to the continuity equation through that. Yeah. 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 Then you need to use a Lagrangian density. You can't. This is a particle Lagrangian. You can't do it through that, I think. I mean, maybe with a Lagrange multiplier. I'm not sure. Okay, so the acoustic metric, I'm just writing its Newtonian limit here. So in the Newtonian limit, the lapse is the sound speed, and the shift is minus the velocity of the fluid. And the null cones of the acoustic metric are the sound cones. In the case, yeah.
The number is not a covariant derivative associated with A, but rather with the space-time metric.
Yeah, this is a usual covariant derivative compatible with Christoffel symbol. So yeah, with the space-time metric, but that metric, is not covariantly constant. So if you take, for example, so this equation is true for any fluid, not just barotropic fluids. It's also true for baroclinic fluids and for fluids that are not irrotational. If you specialize to the case where you have an irrotational fluid, then P is the gradient of a potential, and then you get a wave equation for the velocity potential. And A, it's a nonlinear wave equation in general because A depends on the velocity of the fluid, which is the gradient of S, and on the sound speed. In a special case where if you look at a stiff fluid where the sound speed is 1, then all these nonlinearities go away, and it reduces to a usual Klein-Gordon equation. So that's useful because some tricks or methods are applied for wave equations. We can use them here. Okay, if we do a characteristic analysis of this system, so this equation coupled to the Hamilton equation, we found that there are two speeds that are 0 and two speeds that are v plus minus the sound speed. And that's the Newtonian limit. In the general relativity case, it's more complicated, but it's similar to that. So if you look at the eigenvectors, there's no Jordan block, so this system is well posed, strongly hyperbolic for any sound speed greater than 0, any positive sound speed. Now if you are looking at a polytropic star, let's say as you approach the surface, the density approaches 0 and the sound speed approaches 0, and that the sound cones get more and more narrow, and they degenerate to a line when you reach the surface, and then your system is not hyperbolic anymore. I think it's elliptic on the surface. And so that makes it ill-posed, so not suitable for numerical evolution. Okay, this is a long-standing problem. So you can find a discussion in this paper by Young and Masmoudi, where von Neumann, Heisenberg, Burgers, and others were discussing this in the conference in Paris in 1949. And there's an interesting discussion in this paper. But they were talking about whether the fluid approximation breaks down on the surface of a star and so on. Okay, I will come back to this surface issue. But I talked about the Poincaré-Cartan integral invariant. So generally, this invariant would not be preserved numerically in simulations. I think that if you use symplectic methods to evolve the Euler equation, possibly it may be conserved. But if you don't want to use symplectic methods, you just want to use general methods and still want to preserve this invariant, this is a way to do it is to use constraint damping. So many of you have written papers on this for generalized harmonic gauge and the Klein-Gordon equation. So you already know of what these equations mean. But in this case, so beta is the shift and alpha is the lapse of the space-time metric, and I are the lapse and shift of the acoustic metric. So if you add these constraint damping terms, then you enforce that as you evolve, that the P will be the gradient of the potential. So the circulation will remain zero as you evolve in time. This? Yeah, it's canonical. What do you mean by non-canonical? If it's Hamiltonian, it's canonical. It's the usual Hamiltonian structure of a usual Hamiltonian mechanics. I transitioned from ODEs to PDEs using this chain rule. So that goes from Eulerian coordinates to, from Lagrangian coordinates to Eulerian coordinates. Yeah. Are you talking about formulation that uses Hamiltonian density or Hamiltonian like this? Right. Yes. Yes. Well, that's my question. I don't know what will happen to variational integration once you transform to Eulerian coordinates. Yes. So I mean that's why I'm here. I want to talk about that, but to see if that's possible. But there are variational integrators that are based on Hamilton-Jacobi equations. Maybe those can be applicable here. So, I mean, this is a bit strange compared to classical mechanics because in classical mechanics you have a phase space conservation of that integral, and you have different orbits that are all virtual. But here, all these orbits are actual orbits of the fluid elements, and they are coupled to each other. through H, through the continuity equation. So that's a conceptual difference. But we can talk about that, yeah. Okay, so if the sound speed is 1, so if you have a stiff fluid, then all the nonlinearities go away, and this system will reduce to the usual Klein-Gordon equation written in first-order form. And the usual constraint damping applies. Okay, so some numerical experiments with this formulation. We looked at boundary accretion. So if you have a Schwarzschild black hole and you start with the exact solution of a fluid accreting spherically from infinity, that's a steady state solution. And we start with that solution and perturb it slightly, add a Gaussian perturbation and let it propagate. And we wait some time for the solution to relax and compare it to the exact solution. And we looked at different resolutions. And if you use second-order finite differencing in space, then it converges with second-order accuracy for the Valencia scheme. For the Hamiltonian scheme, you have superconvergence. It converges much faster than you would expect it to. I mean, this is not generic behavior. This happened here because if the Hamiltonian is roughly constant throughout the fluid, as it is here, then if you take a numerical derivative of it, it is exact, even although you use second-order differencing. So you get the exact result, basically, apart from a small region where we have perturbed the fluid. But whereas with the Valencia formulation, that is not exact. You don't differentiate something that's constant in that case. So this is the same experiment, just looking at the accretion rate, which is also constant throughout the flow. So that appears in the continuity equation. So that differentiation is also exact in this case. So this superconvergence may arise when you evolving systems that are close to stationarity. But Franz pointed out that we should try more dynamical cases. And in that case, the convergence is second order for both the schemes. There's no difference. And we looked at the more difficult case. In the end, we want to apply this to neutral star binaries. So we started from looking at the TOV star, spherical star, and looking at radial oscillations. In this case, because the star is oscillating, the Hamiltonian is not constant. So we get second-order convergence for both cases. We had a lot of difficulty dealing with the surface. So the reason, we're not entirely sure yet, but we think that the reason is in the Valencia case, if you look at the flux, it is C1 across the surface. But with the standard atmosphere treatment that people are using. But for the Hamiltonian case, the flux is C0 across the surface. So it behaves worse numerically. So the standard atmosphere formulation is not very good for the Hamiltonian scheme. So we can either modify the atmosphere formulation, use something else, or in this case, near the surface, we just switched the Valencia scheme and just use the Hamiltonian scheme everywhere else in the interior. So if you do this, then you get the correct mode frequencies for the oscillations that you expect for a star of that particular equation state. So I should point out that so the standard atmosphere treatment, I think there are 3 reasons why you need it. Although it may not be obvious. So in the first reason you need it in the Valencia case is that you have rho, you're involving rho u in the continuity equation, and again something times rho in the Euler equation. So you need to divide by rho near the surface, and rho goes to 0 there. So you can't really reach 0, you can't divide by 0. So that's one reason you need it. The other reason is if you approach zero density, then the sound speed goes to zero, then the problem is ill-posed. And the third reason is you need some condition on the surface. You need to reset your quantities on the atmosphere at every time step, so that if you start with a perturbation from inside the star traveling outside, if it reaches the surface, it should be reflected back. If it doesn't do that, then you're not going to get the correct mode frequencies, because you're not going to have the correct boundary conditions. So with the Hamiltonian formulation, you get rid of the first problem, because the quantity I'm evolving is h times u, and h is 1 of the surface. So I don't have to divide by 0 anymore. But it doesn't eliminate the other two problems, which are more serious. Okay. But we're still working on this and trying out different atmospheric treatments. So stay tuned on that. So let's stop here. I should say that, these simulations were run by Ryan Westernacher, and he's also worked on the case of a baroclinic fluid and has done shock capturing and shown that shock capturing works with this method, which is very relevant for the merger phase. But for the inspiral phase, it's a very good approximation to assume that the stars are barotropic. So this barotropic formulation applies there. Thank you. Okay. So I haven't done anything that exploits variational integrations or anything of that sort. And this does not even use the constraint damping yet. But I should say that in this case, we just use finite differencing, simple finite differencing with an RK3 for time integration, and we didn't need anything more. But if we do that here for the TOV stars, we don't get the correct frequencies because although there are no shocks, because of the discontinuity on the atmosphere, on the surface, the finite differences don't deal with that well. But the shock capturing scheme deals with that better, even though it's not a real shock, but it's an artificial discontinuity. But it deals with that better and gives us the correct frequencies. So we use an HLL scheme here.
The breakdown of hyperbolicity that you mentioned as CS goes to 0, that's also present in the Valencia formulation.
Yeah.
I think that's important to know.
Yeah. Yeah.
So it's not like the new system has a problem that the old one didn't.
Yeah, it cannot get rid of that problem just by transforming to different variables.